Thanks for the kind introductions. So here today I will talk about our work at MatBind, which with my excellent collaborators, and let's directly jump into it. So for the motivations, nowadays the discovery of the new materials is kind of very essential for every domains, such like energy materials or robots. And inverse design is pretty important, which you having already in mind what you want, and you want to directly have these materials. And the conventional method is rather slow, data hungry, and often constrained to narrow domains. Apart from that, after you have created new materials, various experiments and measurements need to be conducted to verify the properties and also measure the performance of the materials. It will result into many different results in different modalities, for example, like curves, text, images, time series data. And therefore, naturally, we want to have a model to handle all this heterogeneous data together and guide us for the designs, which give us some requirement for the models. First, we want to have the model which could handle these different modalities, which each modality contains partial information regarding the materials. And we also want this model to be able to unify this partial information together to one shared embedding space, which contains the whole information regarding the materials. And it need also be able to deal with missing measurement, since not all the measurement will be conducted in the real world. And these embeddings would also be able to guide the downstream tasks like classifications, generations. This naturally leads us to the ideas of the foundation models. More specifically, we want to use contrastive learning to train multimodal foundation models. Before I jump into our method, I would first briefly talk about contrastive learning. Maybe you have already heard in the first day's sessions. Contrastive learning was first proposed for get rid of the heavy label tasks. So it's unsupervised learning, which it will augment the images and treat the augmented images as different views of the same images. So namely the positive pairs. And it will view all species other images as negatives. And by the influence losses, it will pull the embeddings of the views from the same image together and push away others. In the end, it will learn the latence of the corresponding images. And MatBind has further expanded these settings from unimodality to multimodality, where it could deal with different information sources, such like images, text, various images like deep sensor data, and also videos, thermal data, videos with audios. And one excellent property of the MatBind is that it does not need all the pairs between these modalities. It just needs the pair between the central modalities and other modalities. In MatBind setups, they have chosen image as their central modalities. So that means that during the training, the pair only needs the pair that between text and images, text and audios are needed, and the direct link between text and audios are not needed. But after properly training, this link will be emerged, which is very ideal for our real-world scenario. Apart from that, the embeddings it learned has also demonstrated strong ability for various downstream tasks, like generative tasks and classification tasks. Therefore, we would like to adapt the settings to our material science, which we will use first use different encoders to encode the different modalities. For crystal structures, we view it as a graph and use graphing network to encode it. For density of states, we use transformers, and for PXRDs, we use ResNet, and for test descriptions of crystal structures, we use MatBind. After we have these embeddings, we will then use info in losses, follow the MatBind setup, We use the crystal structure as a central modalities. That means during the training, only the pair of the text crystal structure, PXRD crystal structure, and those crystal structure are needed. After talking about the models, I would like to briefly talk about the dataset we used. It's a materials project. It's an open source project. It contains roughly around 200,000 different materials, and for each materials, various properties are simulated or calculated. For example, like the band gaps, the PXRD, those. And for our project, we use 4 modalities: the crystal structure, PXRD, density of states, and text descriptions. To preliminary evaluate our models, we will use recall as our matrix. The evaluation will go through all the validation dataset. And to demonstrate the influence of different modalities to our models, we will train with different modality combinations. And it will evaluate through all possible modality pairs. For example, if we train with crystal structures, PXRD, and those, then during evaluations, we will evaluate the retrieval task between crystal structure, those crystal structure, PXRD, and those PXRDs. So here is the evaluation result of recall at once. From the figure, the x-axis is the modalities that we use for training the models. Since the crystal structure is our central modality, so it will be always appear during the training. And y-axis is the modality pairs that we use for the retrieval task. The first one was the query, and the second one was context. So from the figure, you can tell that the link directly shown in the training, for example, link between crystal structure text, crystal structure PXRD are properly shown there. And for the emerge link, which is not directly shown in the training, for example, like the PXRD text, text those, and are properly shown it. One link is failed is the link between PXRD and those. Apart from that, we also have evaluated from another perspective, which we calculate the overlap between the distributions of cosine similarities within the site of the pivotal sky materials and non-pivotal sky materials. And from the figure, you can tell when the PXRD was involved during the training, the model was more capable to distinguish between the pivotal sky materials and non-pivotal sky materials. That means that when you introduce more modalities, it will give the embeddings another perspective of the materials that the other modalities cannot contribute. Then I will use a few brief words to conclude what we have done. So we have proposed a method for material science that follows image band setup to unify different modalities to a shared embedding space. We have high cross-modality recalls, and the emerged relationships between different modalities are shown there. For next steps, we naturally want to further evaluate our embedding space with the different downstream tasks. For example, we might want to do some bandgap predictions. Also very important, we also want to do some generative tasks. For example, like use our embeddings to guide the generations of the crystal structures. And of course, if possible, we will train our model with a bigger data set. Maybe we also want to include more modalities. Yeah, that's all. Thank you.
Thank you so much, Le. Do we have questions? Oh, I see.
Hi, thank you for the talk. I have possibly a very short question. So are all your encoders pre-trained?
Sorry?
Are all your encoders pre-trained?
Only the MatBind is pre-trained. Other encoders are trained from scratch.
Okay, so if some of them are trained from scratch with a contrastive loss, then you are not, I mean, okay, let's just reformulate this question. Have you also considered adding another modality-specific loss into your training? So that you're not just aligning modalities between each other, so you're not just training those ones which are trained from scratch to the ones which are already pre-trained, but you're also having an additional objective.
You mean like additional objective with supervised manner? So for example, like trains also included for example, from dose encoder to predict the band gap?
Not necessarily supervised, more like unsupervised. So if you have like the GNN, for example, it can be trained in unsupervised fashion, but like same as some masking task, for example.
There are approaches from that perspective. So normally, if you train with unsupervised manner, you normally need to augment it, like inside of the modality itself. For example, like an augment the PXRD or dose, which physically a little bit problematic, especially for the crystal structures. But definitely, it is a good way to enhance the embeddings.
Okay, thank you.
Thank you. And we have another question.
Yes. Hi, thank you again for the talk. I have a question. So do you have a protocol or framework in place to kind of ensure the environmental or biocompatibility for the generated materials? So how safe are they in the environment or in living species or something like that? Or do you have information that you could include into the model training for this?
At least from I know, material project does not provide such information if it's like the material is harmful for the environment. Which, if such information was leaked, so for training a model to predict that, additional information is needed.
Okay, thank you.
Then let me ask one more question, because we also have still some time left.
Yep.
Maybe I did not understand it right, or I missed it, but how would the approach work at inference with missing information? So if one of the modalities is not available for whatever reason, would that still work? Or are you bound to having these 4 modalities in place?
Actually, that's one of the strengths of the modalities. So during inference, even there are modality missings. So the model should still be capable to give you the information regarding that. For example, our next step is, for example, you give the crystal structure, and if you directly give you the dose, even it's even not existed, and or the reverse way that you give in the PXRD, it will generate to you the possible crystal structure that's corresponding to it.
Okay, but it would have an impact on the model quality, right?
That need to be further investigated. So for us, we will hopefully it will not harm or jeopardize the model capabilities, because we want to predict the missing modalities.
Okay.
Yeah.
Thank you so much.